So today's talk is, especially compared to some of the other talks in the last couple of weeks, this is a very light talk. This is comparatively elementary. There will be a little bit of working with with higher inductive types, and there will be, most of the rest will be kind of fairly elementary, playing with complex variables, playing with elementary complex algebra. And there will be not much that goes too deep in any direction really in this talk. It's sort of a fun, fairly light interlude. So it's in a way a story that I'll be only giving the beginning of. It's kind of a thread that I started a couple of years ago after we'd come up with the idea of higher inductive types, and worked on a bit with discussing with Mike Schulman, discussing with Christopher Kapolkin, and then sort of let it slumber for a while, and then Guillaume took it back up and nicely finished the job more recently. So he'll be telling you about, he'll be kind of telling you the whole story and taking it on in further directions next week. But for this week, I'll give a slightly different angle, not going on in the type theory, but again, coming back down to the classical complex variables constructions. And so this was just after we'd come up with higher inductive types, trying to say, okay, so as a kind of proof of concept, what are the first kind of non-trivial things we can do with them? Make sure that they really do give some of the non-trivial things that we should expect to find coming up from classical low-dimensional topology coming up in these. And so one of the first things was Mike getting the proof through that pi1 of S1 was Z. And another one was we said, well, classical object of low-dimensional topology that's describable in terms of spheres, cells, and fairly straightforward ways is the Hopf fibration. So we should be able to replicate that in our language. So for those of you who aren't familiar with it, what is the Hopf fibration? So first, entirely classically, if you look up Wikipedia and go to the Hopf fibration, what will you see? Or when you take out the kind of prose and the fluff, what do you see? Well, you can see half a dozen different things. There are quite a few presentations of the Hopf fibration. The key thing that's, the main key thing that's common to all of them is that it's a fibration, and in fact, moreover, a fiber bundle. So a particularly nice fibration. A fiber bundle with base the 2-sphere, so it's a fibration over the 2-sphere, and its total space is a 3-sphere. And even better than that, it's fiber, so its fiber over any point is the 1-sphere, the circle. So base S2, total space S3, and fiber. And since it's connected, the fiber over any point is the same. So I mean, that's kind of neat, that's kind of cute, straight off the bat. But how does it fit together? So what actually is this fibration? One definition is, so there are several definitions, and they each fit, each of the definitions kind of generalizes nicely in different sorts of directions. There are a whole lot of nice directions that the Hopf fibration generalizes in. In particular, for instance, there's a family of other Hopf fibrations that it's called of, but this is a sort of standard member, one that one thinks of as the, and I won't discuss the others for today, but one of the definitions one can take using complex numbers, using the complex representation of S3, so we take S3 as pairs of complex numbers such that the squares of their magnitudes equals 1. And so this, in a way, we're really not using much of the complex structure in this definition. The magnitude of the square of the magnitude of a complex number is the sum of the squares of its components. So in terms of just this description, we can this is pretty much just saying pairs of 4 points from the reals whose squares sum to 1. And so that's certainly one representation of the 3-sphere. But the reason we want to put it complexly is so that we can then tie it into the base. And we'll represent the 2-sphere as the Riemann sphere, so the complex numbers together with a point of at infinity. So I'm going to slightly change this definition in a moment, so don't set in ink just yet. So we could simply say S2 is the extended complex numbers, the Riemann sphere, complex numbers with the point at infinity. Actually, for the sake of what we'll do later, let's set it up a little more symmetrically as mutually inverse pairs from the extended complex plane. So this just makes it a bit clearer how it's symmetric in inverting Z and W. And so now, sorry? Yes. Yes. 0 times infinity being 1 for the purposes of this. Yep. Oh, I'm sorry. C hat. Sorry, extended. I don't mind what notation I use for this so long as you'll allow me to write this.
So you're allowing C and W both to be 0 or infinity?
Yep, absolutely. Any consensus on what's the preferred notation for the Riemann sphere?
Well, the thing you wrote is the projected line.
Yep.
And you mean that 0 times infinity is 1?
Sorry? Yes. So I don't mind what we call this. I want to use the coordinates Z and W like this. So I feel right. So certainly this is a map with total space S3, base space S2. Let's convince ourselves for a moment that it really does have fiber S1. Sorry? Oh, I'm so sorry. I started writing that, and then, yes, that's quite important for saying what the fiber should be. So the map is given any U and V like this. We take their ratio one way round, and symmetrically the other way around. So, so the Z and W for this representation we represent in terms of U and V. And we'll be, just in terms of this kind of way of specifying the map, we'll be later on coming back to a lot of sort of small spaces represented as subsets of the complex plane in these kind of ways, and representing a lot of maps between them by going between named coordinate representations in this sort of style. Yep, yes. So using the naivest and crudest things that one could do with 1 and infinity in this. And in this, we're not even beginning to go near the places where that would break down or go horribly wrong. We could write out the half dozen special cases that we need. So this is the one of the classical constructions of the Hopf fibration. And let's quickly check that the fiber is S1 given ZW equals 1, we want space of UV such that U squared plus V squared equals 1 and U over V equals Z. For this purpose, since the Z and W are mutually defined, we can the W condition is equivalent to this condition, so we can forget it for a moment. Well, let's see. So this is equivalent to pairs sorry, this is equivalent to just V such that ZV squared plus V squared equals 1. And simply substitute out for U. But this is now equivalent to 1 plus magnitude Z squared all times V squared equals 1. This is equivalent to saying that the magnitude of V equals one of the root of Z squared and so we can now say, yes, this is isomorphic to the circle, except, hang on, we should have been careful, because this step we were naughty. We did what every undergraduate is told they can't do, and we implicitly, in this isomorphism, were not careful about whether we were dividing or multiplying by 0 or infinity. So, as long as and so this works as long as which way around? As long as Z is not infinity, or equivalently, V is not 0, this works. So if Z is not infinity, then all of this works. If Z equals infinity, then switch to W and do the same thing the other way around with W. So either way around, we have this argument that works if Z is finite. The other argument, switching U and V, works if W is finite. So in any case, the fiber comes out to be S1. And if you have an eye on the fact, the question of kind of how far one should expect fibrations to trivialize, it should be no surprise that we had to, in some sense, split up between W and Z and get an argument which was not continuous over the whole sphere. If we'd got through to this stage without having to stop and say, oh, hang on, check by cases at some point, then we would have come very close to constructing a isomorphism of the fiber with S1 which is continuous in the base, and so trivializing the fibration, which we don't want to. So this is kind of quick classical review of what the Hopf fibration looks like. Any questions looking at that before I move on to what happens when you come at it from higher inductive types? Good question. Because it's there is one thing. Because it ends up being very helpful for understanding the relationships between spheres and hence between homotopy groups, and in particular between homotopy groups of spheres, but in general relationships between spheres and homotopy groups. Also, and various geometric phenomena come up, and one can get them analyzed through this. I don't.
First example of homotopy group of sphere, where the number of the group is strictly greater than the dimension of the sphere.
Yes.
The first example of a situation when 0, while homology is 0.
So this comes in that this gives a map from S3 to S2, which gives a non-trivial element of pi3 of S2. And it takes a little work, but not too much to get that from this.
So we can see that pi 3 of S2 is not trivial.
Yeah,
Right?
yeah, because this map is not homotopic to a constant map, which is sort of surprising.
And neither is any suspension of it. It's kind of weird. You could generate lots of them.
Do you want to try to draw a picture of it?
I wish that I could try to draw a picture of it. I don't think I really can draw a picture. There are nice pictures on Wikipedia and elsewhere on the web which have things like sequences of interlocked key rings and those kinds of things, but I won't try and draw one now. If anyone can suggest something to draw.
If you think of S3 as R3 with a point to infinity, then you can foliate it into tori. So there's one torus, and then it sort of fattens up and heads off to infinity, and then it sort of slims down and heads off to infinity. So there's a single circle, and then there's another circle, which is like a line, a vertical line that goes through infinity.
Yes, that's one way. Yeah. I think that is certainly one of the pictures one can aim for. Again, it's beyond my blackboard skills, I'm afraid. But yeah. So this is classically the Hopf fibration as one might quickly see it. What happens if we say, okay, let's come at this from higher inductive types, we've just defined higher inductive types, how can we try and build the Hopf fibration? Well, all right, so let's quickly remind ourselves what are the relevant higher inductive types. We have S1 is generated by base 1 is in S1, and then loop 1 is a path from base 1 to itself. Where's the chalk gone? So S2 is the same, except that the loop is a 2-cell. So we have, again, a base point. And loop 2 is a path from REFL, an identity path on base 2 to itself. S3 we won't end up looking at as a higher inductive type in this talk, so I won't give that for now. But when Guillaume takes the story further, then absolutely he'll be looking at a version of S3 as a higher inductive type too. So we want a fibration over S2 with S1 as fiber. Let's see, so what kind of thing are we even trying to write in the type theory? We're trying to write a map from S2 to type. So a map from S2 to type is exactly an instance where we can bring out the elimination property for the higher inductive type. We're mapping out of an inductive type. So it's given by the fiber over the base, which in this case is, well, we know what we want the fiber to be over any fixed point. We want it to be S1. Great. And then we want that the action on 2 cells of Hopf applied to this loop should be something of the sort. What type should it take? It should be a path between refl S1 and itself in paths in the universe from S1 to S1.
Remind us what the elimination rule is.
So, right. So generally, a map from S2 into any type X is equivalent to an element of X to be used as the image of base, and then a path from refl X to refl X inside paths from X to X inside the type big X. So to map from the sphere into any type, you need to give a base point and then a two-cell in the type between refl of it and itself. And so in this case, the type that we're eliminating into is the universe, or a universe of types. And so we give an actual type as the fiber over the base point. And then we give a two-cell in the universe. And what is a two-cell in the universe? Well, at this point, if we don't make an assumption something like univalence, we're stuck, because we don't, in just plain old type theory, know anything about what the paths in the universe are. But under univalence, we know very nicely what they are. So assuming univalence, we have that we know that S1 equals the qualities between S1 and S1 in type are equivalent to equivalences from S1 to itself. And so what we want as a second part of the eliminator here is a path. So we're looking for a path in equivalences from S1 to itself. And what's it going between? Well, it goes, its source and target are both whatever the reflexivity corresponds to under this equivalence, and that's exactly the identity equivalence. So the identity equivalence, which let's call it for now little id. So we want to path in equivalences from there to there. But now again, this is all equivalent to firstly, paths between two equivalences in the space of equivalences are the same as paths between them in the space of functions, because equivalences, being an equivalence is just a property of a function. So the inclusion of equivalences into functions doesn't change what the paths are. Another way of looking at that is to say that if you've got two equivalences and a homotopy between them as functions, that then every point on the homotopy is again an equivalence, because each point on it is homotopic to an equivalence, so it's an equivalence. And so that's a path between them in the space of equivalences. So this again is equivalent to paths in the space of functions between these things. And paths between functions, by functional extensionality, that's the same as pointwise equalities or homotopies, which we're using as double equals, I think, in the library last time we looked. So let's write it by a long equals for now. So what we need to give for the second part of here, a homotopy from the identity on the circle to itself. And generally, this would happen whether we'd started with a circle or any other space. We didn't do anything particular with the circle in here. Generally, a fibration over the two-sphere corresponds to a choice of the fiber over the, and then a homotopy from the identity on that fiber to itself.
You don't want to say a loop?
So, I mean, we could say a loop in this space. I mean, it certainly is a loop.
Well, it's equivalent modular functional extensionality, right?
Yep. Yep.
It's, I'm sorry?
It's equivalent modular functional extensionality. Either
Okay.
distinguishing the homotopy between functions and a path in the space of functions.
Okay.
So in type theory, one can be slightly careful about this.
Yeah.
Yep.
But given any values?
Yep.
Yeah.
Yep.
You said that it's true more generally for any object type. Instead of S1, you could take a type T or something.
Yep.
And then you're saying that a map, yeah, would be produced by a loop from the identity to itself
Yep.
in the space of equivalence or self-equivalence.
Yep. Or even just in the space of functions.
Do you have a name for the space of self-equivalence or something like that? Because you will write equivalence S1 and S1.
Yep.
I don't know in the formal type theory if you have. Because in mathematics we like to distinguish automorphism from isomorphism, right?
And certainly there's a good tradition of writing this.
I would be happy with that because that's.
I can say what equivalence.
I'm sorry.
What equivalence?
Self-equivalence?
Auto equivalence, like automorphism.
Auto-equivalence. Why not? It's a bit longer, but why not? Yeah.
I don't know. On the one hand, I don't know. Some mornings I would feel like writing this to distinguish the fact that it's autoequivalence or something. Other times, it's nice to keep it like this, just to emphasize the fact that this is simply an instance of a more general notion. I mean, the philosophy that there's nothing special about groups compared to groupoids. There's
I see.
one
You're
can.
not using the fact that the
It's a-
composition of the whatever, you're not using the structure.
But even if we were, we could see it as being from the general groupoid structure on equivalences rather than specifically from the group structure on autoequivalences. So it's I don't know. I don't have strong feelings one way or the other. We can call it either.
But the point was that a fibration on the two-sphere consists of a type together with space of autoequivalence.
Yep.
Morphisms of this pattern.
So generally,
Not an
yep.
automorphism of the fiber, but a loop on
Uh,
the length in the space. Well, a loop is out. So not just an element in out. Yeah, a loop in out. A loop is out of T. A loop from the identity to the identity is out of T.
You know the
Yep.
I1 of the of endomorphism.
So corresponds with
I1 at the identity.
Yes.
so. Or in slightly more elementary terms, a homotopy from id x to itself, since this is.
The more elementary term is the proof that id x equals id x, right?
Yes. So that's slightly more elementary terms to stay, but this is the one which is typically more elementary to give, because this homotopy is saying for every element of x, a path in x from that point to itself. By functional extensionality, they're absolutely the same thing. All of these are the same thing. So we're also giving, one way to look at it is a natural loop at any point of x. A natural loop over x.
You're saying an element in that type.
Yep. Yep. So in particular, for the Hopf fibration, we're trying to give one of these things for the circle. And so, just looking geometrically for the moment, we want, let's draw a picture and convince ourselves of what we want. We want a homotopy from id S1 to, shouldn't switch notations, the identity on S1 to itself. So what can we do? What's a natural homotopy from the identity on S1 to itself? You've got the identity on S1 is sitting there. You want to move it around somehow in such a way that after you move it around, you've still got the identity. Every point's the same place as it started.
Can you just not move it?
You could certainly just move it. And that's always an option. That's something that that's kind of the most natural and straightforward thing one can do. We could do that for any type x. There's always an inhabitant here, the reflexivity type. And so that's something nice. It's something we can always do. But what it gives us in the end is that gives us the trivial fibration whose total space will just be equivalent to S2 cross x. So that's certainly something we can do. But in this case, we need something which is going to end up non-trivial and specific to the fact this was a circle. So that's, I think, the simplest thing we can do. But it's not quite enough to give us something, give us what we want. So Dan's setting about saying, exactly, we can take the circle and we can spin it. We can spin the steering wheel once. We can say, at time 0, it's sitting there like this. As time goes round, we spin it like this. And then after a spin, we've come back to where we started. So that gives a homotopy from the identity to itself. And notice we could also have chosen to spin twice, or spin 5 times, or spin minus 17 times, or whatever. But spin once is a fairly natural place to start, and spinning 0 times would be your suggestion. So intuitively, it's clear that there's a very natural choice of non-trivial homotopy here. So yes, we could spin backwards once just as well. If we well, we've already broken the asymmetry by choosing our loop here. So if we hadn't broken symmetry somehow, then we'd have to do so here. But we already have in this case. So. Yep. So.
Would that be like switching the roles of Z and W?
I don't know. When we chase through that to see how that comes out as this, then let's return to that. And quite possible. Good question. Let's come back to that. So there's one clear non-trivial natural natural candidate. So yep. This is probably a good moment.
Well, it strikes me suddenly that somehow the circle that you have defined is an oriented circle.
So the paths are symmetric in the sense that there's an isomorphism between paths going one way and paths going the other. So in the same sense that in higher groupoids, an arrow in the groupoid, it does have an orientation. On the other hand, it's equivalent to an arrow with the opposite orientation.
Yes.
So oriented in the same sense that many presentations of higher groupoids are oriented.
Yes, but it seems that just the definition itself is providing some kind of extra structure on the homotopy type, which you may want to get rid of by looking at it in a certain way, but you may preserve it if you want to, which means that you could actually put some orientations of your homotopy type or whatever. It's just a trivial observation that they gave.
Okay. Yes, I'm right.
I was going to say that the circle is sort of freely generated by a point in a loop, so it has some universal property. But maybe what you're saying is that it also has that same universal property in a different way. It's also generated by the base and the inverse of the loop.
Sure, because the circle with the opposite orientation is actually the two are isomorphic.
Yep.
Isomorphic with respect to an isomorphism which reverse the orientation. So, but if you want to keep the orientation, they are not isomorphic. So, in other words, there is a way to put the orientation there if you like, but it's not so important. And this is what you're doing here because you want to say, I'm going to choose a certain generator here, and you're picking one, therefore you're actually using the orientation.
Okay. Right. And
I was going to say, you actually, I mean, you should be a little more formal, right? I mean, in fact, the functions from S1 to S1 by the elimination for S1 are given by a pair, by pairs, the point and the loop, and in S1.
yep.
So you need to find a loop in this space of pairs.
Absolutely. So I mean, I'm sorry. I mean, I'm not saying this is directly what I would type into Coq. This is there are if we want to type this into Coq, then or Agda or whatever, there are several points here where my one line would become 5 lines, and also saying from spin once, we have to unwind this description of spin once using the elimination property of the circle to get an element of that type, and I'll go in that direction in a moment. Yep.
So this is the reason why the trivial, and the remark by Vladimir is the reason why the trivial vibration is not good. Why the trivial choice is not good.
I wouldn't say the trivial choice is not good. It doesn't give the Hopf vibration. It gives a different vibration. Yep. I mean, it gives a good vibration over here. It just doesn't give the Hopf vibration.
The total space of the vibration won't be the 3 spheres of this.
Yep.
Okay. It will
Yep.
be S2 cross S1.
Yep.
With the product.
Yep. Yes. So. Let's see. So, yep. So as Vladimir said, we've saying spin once isn't enough to really check that we actually can define this in the type theory. And if you're going down the type theoretic road further, what you'd do would be say, well, we're trying to produce something of this sort with x equals S1, so we break down using the universal property of S1 and show that we can create something which is which implements our geometric picture of spin once. But I'm actually not going to go any further down that road. What I want to do is chase back and say, and just do a sort of plausibility argument of why this now, I said to Eve that if we chose the constant homotopy, that would give the wrong total space for the fibration. Okay, well, why does this give the right total space for the fibration? Why does this homotopy correspond to the right thing to give that classical fibration we wrote down earlier? And so I want to chase back to the classical world and see how this correspondence of what fibrations over the two-sphere are, see how that classical correspondence arises in the classical setting, and see concretely what it's implemented as, and then see why, under that correspondence that we've explicitly constructed, this fibration does indeed correspond to the spin once homotopy on the circle.
So in other words, you want to show that the
So,
model of the critical spaces.
yeah, so I won't formally show that, but it will at least give a plausibility argument for that. So since the topological model has many difficulties, and I'm going to work topologically, so what I say and work with won't, at least not in any way that I know of, be an actual formal model for higher inductive types, but it'll be a plausibility argument for the way that higher inductive types should interpret something like this, and how under a correspondence that looks like a plausible interpretation of this, the spin-once homotopy will correspond to the Hopf vibration. So the to-do next is persuade ourselves that this corresponds classically to the Hopf vibration. So we want an explicit correspondence in the topological world between fibrations over S2 with a given fiber X and homotopies from, let's move now to a more traditional notation, homotopies from the identity on X to itself. And this is, not surprisingly, this isn't something which, this correspondence isn't something which we were the first people to ever think of. There are, it appears in various guises under various names in various different areas of the literature. I haven't actually been able to find a kind of single clear statement of exactly this lines that with some clear name attached to it. But there are a lot of principles that are similar to this that imply this, that have it go back and forwards.
In the book of Steenrod, it's probably
so is the
Steenrod looks at fibrations over spheres.
okay.
He has descriptions very much like
Right.
that.
So what was the title, sorry? So yes, I don't know the literature well, so there are, I absolutely, when I say I haven't found anywhere with this exact statement, that's certainly not saying it isn't there. This is one place it could be. Other analogous statements or analogous places where this sort of principle comes up are with vector bundles. They're described in several places in terms of clutching functions, and that's essentially exactly this in the linear algebra world. and another. Essentially, so if one was constructing vector bundles instead of fibrations or fiber bundles, then this homotopy would become a loop in the GL of the vector space that was used as a fiber. And so, yep. And yes, and another version is that this can be unwound from statements of the form which that fibrations over X with fiber F in some sense of that is equivalent in some sense to classes of maps from X into the classifying space of the topological monoid of autoequivalences of F. And this is actually one of the closest things that I know of in kind of classical approaches to algebraic topology to a very univalency type statement, saying that fibrations are equivalent to maps into some space of types, since one can see the B of aut of F as a universe of types that are equivalent to F. So this is these are sort of classical functions that imply the versions of these imply correspondence of this sort. But let's actually, I said this talk wasn't going to go too deep in any direction, and getting into these would count as going reasonably deep, I think. And I'm going to be much more naive, much more explicit, and just write down decompositions of spheres and concretely work out how we can go between things of this sort. So, and one can check, of course, not surprisingly, that if one takes certainly any of these, and presumably that, and unwinds it, beta reduces it down to something concrete, one gets what we're about to give. So, we're going to unwind this very concretely. So let's look at the sphere itself, S2, and we can see the sphere as it's got a northern hemisphere and a southern hemisphere, and they intersect in the equator. So the northern hemisphere in itself, when we delete the southern hemisphere, just look at the northern hemisphere itself is just a circular disk, a two-dimensional disk. So it's a D2, which let's call it D2N for the northern hemisphere. D2 south for the southern hemisphere, and the intersection is a copy of S1. So this square is a pullback, and it's also a push-out, because we can see the sphere as the thing is glued that way. So we won't follow this that far, but it'll be helpful for a little while. Let's put a base point in as well. So we're thinking of the whole thing as a based space. Since we're thinking of fibrations with a given fiber, if we're thinking of fibrations with a given fiber, to make sense of that, we want to mean what we want to mean by with fiber x is to say there's a base point here. These are fibrations together with over the base point, that fiber being isomorphic or equivalent to x. So that's a sphere. And suppose we've got a fibration over it. So I would really like the diagram that we're about to draw here to be above that diagram there. And it will be in a moment when I put the blackboards back, but I'm not quite tall enough to draw it up there. So suppose we've got some fibration E living over the two-sphere. Then, certainly for a start, we can pull it back to its restriction over either of the hemispheres. Actually, let's leave a little more space on the left. And its restriction over the equator. This will certainly always be a pullback, and under reasonable hypotheses on the space involved in the fibration, it will often also be a push-out. So certainly, if this is a fiber bundle, that will again be a push-out, and indeed, in the case of the Hopf fibration that we'll get to, we will have every nice hypothesis we could possibly eat. So in that case, it's a push-out. But generally, it might or might not be a push-out, but it'll often, but under reasonable hypotheses, it will be. So we've got this. What can we do with it? Well, the nice thing here is that the disks are contractible. Oh, and let's put our fiber in there to start for a moment. So if we look at either of these fibrations over the disks, the disks are contractible, and any fibration over a contractible space is equivalent fiber-wise to a trivial fibration. So let's see what we've got. Given E over S2, look at E restricted to the northern hemisphere over the northern hemisphere. Since this is contractible, we can find a fiber-wise equivalence between this and the trivial fibration. Let's call this phi sub north.
Just not to confuse people, the trivial fibration here is a completely different from trivial fibration.
Oh, yes, thank you very much. That's a very good point. Trivial bundle, maybe it would be a less ambiguous word for it. Yep, absolutely. Constant fibration is good if we're thinking of fibrations as mapped into somewhere. So trivializing E over D2n. So we have we have this fiber-wise equivalence phi sub n with D2 across the fiber, and we can do the same thing, of course, on the southern side, exactly symmetric. And let's see, and when we pull these, when we pull these back to further to the equator now, we'll get that this is isomorphic to the equator across that. Right? Not right, because it's very, very, very tempting to write this for a moment. But we have to be a bit careful, because certainly when we pull this back here, we'll get something which is S1 cross F, and this will pull back to a 5-wise equivalence with the restriction of E over the equator. And certainly when we pull this back, we'll get, and now let's take this move that a little bit out of the way. When we take this back, we get a copy of S1 cross F and an equivalence of it with E restricted to S1. But they may not be the same. There's no way to know that. We can't see from what we've got here that they're the same. And in fact, we don't want to, because this turns out to be the heart of our correspondence, the key to our correspondence, that we've trivialized our fibration in one way over one of the hemispheres and another way over the other hemispheres. And on the equator, our two trivializations might not end up matching up. If they did, we'd be able to trivialize the whole thing, but they might not end up matching up. And so let's look at what we have got here. So we end up with, when we So comparing the trivializations over the equator, we have, all living over S1, we have E restricted to S1, we have S1 cross F, and we've got this equivalence, which is coming from phi north restricted to S1. And then we've got another equivalence coming from phi south restricted to S1. So cutting out the middleman, and inverting one of these, since in the construction there was enough data that we were able to construct if we wanted homotopy inverses to these, we have something which we'll call phi. So a fiber-wise equivalence between S1 cross F and itself over S1. And also, we can be just a little more. We had our base point here. And we did know from the data in our diagram that each of these trivializations were chosen to commute with the base point. And so at the base point, it does commute. So we've got a fiber-wise equivalence, but that's exactly saying for each point in S1, we've got an equivalence from F to itself. So from each point in S1, you have an equivalence between the fibers. So from F to itself, so let's call this total map phi hat. And over at the base point at time 1, let's say, we know that this commutes with those, and so there, it's the identity. So with at time 1, it's 1f. So this was these all commuted with the base point. So we've got exactly a self-homotopy of the identity on F. So this is very far from being a proper correspondence in any careful statement of the sort between these things. We took something over here, we took a fibration with that right fiber, and we constructed a self-homotopy. We didn't check, and we won't, that it's well-defined up to any reasonable notion of equivalence. We didn't check how the inverse goes. But one can chase those through, and those all do go through. One can say good things along those lines in all sorts of ways. Just as an example of the kind of thing, one of the places where we made what seemed like an arbitrary choice was the trivializations over the north and south hemispheres. But again, by contractibility, those trivializations are well-defined up to fiber-wise homotopy. So they're not uniquely canonical, but they are canonical up to fiber-wise homotopy. And if we'd pulled those fiber-wise homotopies through, they would have told us that we got two chosen homotopies which were themselves homotopic at the higher level. So up to homotopy, what we got here wouldn't have changed. And each of the places where we made some kind of arbitrary choice, one can say something like that. But we've unwound, so we've unwound a kind of underlying map which underlies one direction of this correspondence. So this gives one direction of the desired correspondence. And what I want to do now, rather than checking that it really does lift to a full nice correspondence, is to simply say, so if we started with the Hopf fibration here, what do we get? We know what we hope we'll get. We hope to get the spin once homotopy. Do we really get it? Maybe just before going back, it's worth saying a very quick word about how the other direction of the correspondence would go. That if we were given this the phi, or equivalently phi hat, to start with, then we would have kind of everything, the outer part of this diagram and not the inner part. But now this corner was essentially equivalent to that outer corner. And we said that under nice conditions, the total space E could be recovered as a push-out of its restrictions to the three different parts of the sphere. And so if we have, instead of exactly these, we have this kind of three-step span here, again, we can take its push-out, and that gives us a fibration over the whole sphere. And that is how, from a map of this sort, we can recover a fibration over the sphere, which then, when one goes back, will give back the map we wanted. So the other direction of the correspondence is taking push-out, taking two copies of F across the disk, and gluing them together along the boundary of the disk according to the equivalence, according to the loop of equivalence that we've specified here. So that's how the other direction would go. But now if we take this direction and see what it gives when we start with the Hopf fibration as we had it earlier. And let's for a little bit turn it this way so that we can just coordinatify, first of all, our sphere. So we have, putting a sphere well in the middle. As a sphere itself, we are representing that as pairs Z and W from C infinity, may I call it that, such that ZW equals 1, mutually inverse pairs from the Riemann sphere. Then C hat, right. Okay. I'm not familiar with that notation for it, and I keep reading it and thinking pre-sheaves, so if I accidentally call these pre-sheaves now at some point, my apologies. So the two hemispheres now correspond to the unit disks in Z and in W. So this is, actually let's go a bit more space. So this is Z such that the absolute value of Z is less than or equal to 1. And we map in there by taking W to be 1 over Z. So here's a convention which is going to go all through the big diagram that we're going to be constructing, which is that any parameter whose type is not given is a complex parameter, a plain complex parameter. So, and over this side we have the unit disk in W. And we go along here by setting Z is 1 over W. And their intersection we could describe.
You have E divided by W over there inside the curly bracket.
I shouldn't anywhere. This is Z times W. Sorry. Yeah, straight bit of chalk. Thank you. And now for their intersection, we want the unit circle. What representation of the unit circle should we use? I'll again have a parameter of a different type and take so just for the sake of, again, trying to be a bit more symmetric in W and Z, let's use a completely different parameter, call it T for the circle. And so on this side, we take the unit circle Bedian by setting Z is e to the T. And then on this side, we want to set, so we need to end up with Z and W being mutually inverse. So we set W is e to the minus T to give the embedding from here into here. Yes, I do. Thank you very much indeed. Thank you. Thank you. That's good. Yes, otherwise it would have given not quite the unit circle. So, once again, I guess I should swap these boards to parallel those boards. Once again, I'd like to be drawing all this diagram above all of that. But there's, again, I'm certainly not quite tall enough when we're writing a lot of different complex things to parameterize different bits of the Hopf fibration. So the Hopf fibration, again, we took by parameterizing the three-sphere as pairs of complex coordinates, u and v, whose magnitudes together summed of squared to 1. So pairs u and v, they're complex, so let's not even bother saying what they are, whose magnitudes sum to 1. And then the map from here down to there goes by setting Z is u over v, w is v over u. So then on the left, when we pull this back to the left side, we have, we get everything in here such that it's Z, it has magnitude less than 1. So this is u and v is such that magnitude of u squared plus the magnitude of v squared is 1, and the magnitude of u over v is at most 1. And let's work just on the left-hand side for a bit and do a bit of work over there and then simply say, well, the right-hand side will be the same. So we'll work just on the left-hand side for a little bit. So we've got this on the left, and we want to trivialize it. We want to show that it's isomorphic to the unit disk there, cross with the circle. How can we see that? Well, first we can write this as, let's do this calculation on the side for a moment so that we can bring it back without the intermediate steps to clutter the diagram a bit less. So we have pairs u and v whose squares sum to 1, and such that the magnitude of u of v is less than 1. So now we can rewrite this with this thing being called z. And since we aren't in the case where this could have been infinity, we know it's smaller than 1, so it's a genuine, honest, complex number. So this is, from z and v together, we can certainly recover u. So this is pairs z and v such that zv squared plus v squared equals 1, and z is smaller than 1. This is going into the right direction because we've got one of our parameters now to be something coming from the unit disk. We now just want to wrap this other parameter into being from the circle. So we can factor this out a bit and get that this is, again, 1 plus z squared v squared is 1. Similarly, this can be written as that the magnitude of v is root of 1 over 1 plus z squared. And so this is, so we can rewrite this as, this is equivalent to saying that we've got some, that magnitude of alpha is 1, where alpha is the root of 1 plus c squared all times v, and similarly v is alpha over that root. And so this space is isomorphic to pairs z alpha. So via this correspondence between v's and alphas, this space is isomorphic to pairs z alpha, where z is in the unit disk and alpha lies on the unit circle. So this is exactly a trivialization of the form that we want. We moved it, and we should be careful to check that the notation kind of took care of it for us. We want the trivialization, the isomorphism between this and z alpha we want to know that this was over the disk that we were working fibrantly over. But that's taken care of by our notation. Whenever we're reusing a parameter here, like z up here and z in the disk, then implicitly the maps are acting as the identity on that parameter. And so now from here down to the z gives the same as here into the z and then fix the z.
Dependent types.
Sorry?
Dependent types. You're using the z
Probably.
in the base.
Yep.
And then it occurs up in the dependent type again, the same z.
I suspect one probably can. Yes, one probably can. Yeah, something like definitely. So let's keep track of our formulas because we'll need them again in a moment. We had that here. Z was, well, we already know that Z is U over V. Here we had that alpha was root of 1 plus z squared times v, and v, and going this way, then v is alpha over the root of 1 plus z squared, and then u was equal to v times z. So that gives us our trivialization, and on this side we can do the symmetric thing. So this is uv such that they're squares, are 1, and v over u is smaller than 1. And then this is isomorphic to w beta, where, what did we have? We want something symmetric to that. So start, w is in the unit disk and beta is on the unit circle. And the relationship was that beta should be root of 1 plus w squared times u. U should be beta over this square root, and then v should be uw. So now we pull them into the middle, and over on here we have uv such that u squared plus v squared equals 1, and when we take their quotient either way around, we get modulus 1. So equivalently, we can say that they have the same magnitude. When we pull this back, we get exactly z alpha such that they both have magnitude 1, except let's reparameterize z in terms of t just like we did in the base. So this is t alpha such that where t was in R of z and alpha was on the unit circle. And we have that isomorphism given by the same formulas as across there. And in this case, we have t in R of z and beta, where beta's on the unit circle. So we've got the whole picture in place now. So we want to see how it corresponds to a homotopy. So we can put these big diagrams living over each other as they should. And does anyone mind if I erase this board now for the homotopy? So let's see. So so what we have now is S1 cross S1, S1 cross S1 all over S1, where this is a little bit confusing to read because of the fact that the different S1s are coming from different kinds of things. This second one is from the fiber. These ones are all from the base. These ones are all essentially the same one, and we're always using the first projection. So in this picture, what's that come out to? We've got T alpha and T beta all over just the coordinate t. And so we want to unwind this to map from S1 to automorphisms of F in other words, for each t, we want to see how the map relates alphas and betas. So given t, how does alpha map to beta? And now it's just formula chasing. We have that given t, if we say we want to say what's beta in terms of alpha. So we start up at the definition here on the right and chase kind of around the circle and come back to alpha on the left. So beta we can give in terms of w and u. So beta is root 1 plus w squared u. Unwinding that, let's see, w we know is e to the minus 2 pi I t. But that, we don't even need to know too hard that it's e to the minus 2 pi I t. We simply need to know that its magnitude is 1. We're on the unit circle. So this is root 2 times u. What was u here? U was beta over the root of that. So, wait, that's wrong. Yes. No, yes. Which was the? Sorry. Which is the? Sorry. Yes, I know. No, actually, I'm going. U is VZ. No, this is if. Yep. So u, I guess. We know what. How do we do? Sorry, I'm having blackboard syndrome, so help is very gratefully, very, very welcome indeed. I have notes for this part somewhere on my computer, but we shouldn't need them. It is certainly chasing around the circle. One of you see it before I pull them up on my computer. Okay. Yep, absolutely. So you read the next line off that I was about to come back with from the commuter. So u is v times z, and now here z we know what it is in terms of t, and v we know what it is in terms of things involving alpha. So this is root 2. So and z was, what was z again? E to the 2 pi I t. So we have root 2 alpha over root 2 e to the 2 pi I t. So beta is e to the 2 pi I t alpha. And so this is exactly the homotopy we wanted. At t equals 0, this says that beta is exactly alpha. And then as t goes up through, this factor that we're rotating by goes around the circle and comes back to at t equals 1. Again, we have the identity. So this is exactly what we wanted confirming that indeed the Hopf vibration of this correspondence does correspond to the spinning once. So, thank you.